Nowadays, the use of Python is getting popular, mainly because it's user-friendly and saves quite a lot of developing and debugging time. There are several techniques that can be applied to speed up Python codes. The goal of this project is to investigate optimizations for Python programs that run not only on CPUs but also on GPUs. The base code of this project was developed in last year's summer of HPC by Ebru Delage. The investigated program performs a computational fluid dynamics simulation. In this example, the cavity is a square box with an inlet and outlet on different sides. The problem is a continuous system and can be described with a modified Poisson equation. For the simulation, it needs to be discretized with a grid. Iteratively, each tile is updated using values of the neighboring tiles. With a scale factor, the size of the grid can be altered and therewith the accuracy. For increasing the performance of a program, one does not always need to switch to parallel methods. One can start with simple things like choosing the right implementation of a function. The square of a matrix A can be computed in at least 4 different ways: a for loop, the NumPy power function, the Python power function, or a multiplication. In the graph, the execution times of those implementations for different sizes of A are compared. The simple multiplication may be up to 100 times faster. The next step could be the binding of C code. PyBind 11 provides an easy way to add compiled C++ code to a Python project. In the C++ code, a binding method is added after the functions to generate a Python module. After compiling the code, the module can be imported in Python and be used. In this project, the execution times of the new module and the pure C++ functions are about the same. They are about 10 times faster than the implementation with NumPy. To further increase the performance of the function, parallelization techniques like OpenMP can be used. The C++ code has to be slightly altered, but no changes are made in the Python project. Using OpenMP with 18 threads can boost the performance again by a factor of 10. Examining the OpenMP, a performance cutoff can be seen at 36 threads. This equals the threads on one processor. On this system, one node has 2 processors. The memory is allocated with Python close to the processor executing Python. The access to the second processor to the first memory throttles the system. A different allocation method may resolve this problem.
Now, before moving on to some more optimizations for Python, let's take a look on the performance of the baseline Python code, which uses NumPy to make the matrix calculations. The curve, representing the iteration time, becomes almost vertical for a relatively small scale factor. The C serial code is somewhat faster, but also not optimal. There is a Python module named numxpr, which turns out to make the calculations faster than the NumPy module. numxpr uses multi-threading internally, so before running the Python code in parallel, it is wise to examine which combination of MPI processes and threads per process is the most optimal. After running tests on both x86 and ARM-based supercomputers, it seems that the best option is to use as many single-threaded MPI processes as possible within a compute node. With that conclusion in mind, the optimized parallel Python code now takes the least time to complete, and it is even leaving the C parallel code behind. The next thing is to use the GPU to run both Python and C codes. For Python, NumPy-CUDA module was used to implement the GPU version, but it merely manages to surpass the serial codes, being nowhere near the CPU parallel performance. On the other hand, CUDA-C program outperforms even the parallel versions. In this particular code, only one kernel is launched, using the CUDA Runtime Launch API to avoid the overhead of launching multiple kernels on the GPU. However, this overhead is minor, and because of the fact that the API applies some limitations to the amount of GPU blocks, it is quite faster to launch multiple smaller kernels in the standard way. To conclude, there is a number of ways to improve the performance of Python codes. On the CPU, it can be done with predefined libraries or added C modules with PyBind 11. The resulting performance boost can be compared to, or sometimes even outperform, pure C code. On the GPU, the NumPy-CUDA for Python does not help to obtain a comparable speedup. However, the C code can be drastically outperformed by using the CUDA-C programming model, which achieves 30 times better performance. Thank you for listening to our suggestions on how to make Python code faster.